So overview of conic sections. There's going to be basically one concept idea that will be on the final exam related to this that we'll go through pretty much on the last slide. Before we do that, we're going to do a couple review problems. So for conic sections, what I want you to visualize, don't write this down, just look at it as we go through this. But imagine, if you will, we've got this vertical line, this X value here, this black line that's going up and down as an imaginary line of symmetry. And I'm taking this line, and you got to imagine that we're in three-dimensional space right now. And I'm going to take this red line that's going to intersect this line of symmetry at that one particular point right there. All right. So the way to kind of visualize this is if you have like a long stick or something beyond, like, I don't know what you else have besides a long stick, something that's going to be rigid like a line. And if I hold that stick at one point, I can do some things with it. Like if I just take it at one point and I just spin it, just like this, and it spins around in a circle, that line, if you thought about what it would create in geometry, it's going to create a plane. Because if I had an infinitely long stick, and I had it like at one point and I was balancing it and I give it a big spin, it's just going to spin in this big flat surface, making a plane. What we're going to do today, though, is we're going to take it, and instead of spinning it completely like this, we're going to have it like semi-off balance, and then we're going to spin it so that this spins around in a circle. That's really a terrible circle. I'm going to try to redraw that. Around that line of symmetry. So if I can take that and do it a little bit better this time, and take this and rotate it around this line of symmetry, so that that top of that line spins around the circle like this, but it's hinged right here. So then the bottom, what's going to happen with the bottom? It's also going to spin. I'm going to do it like that because it's going to create this three-dimensional space. Where what I end up with, when I spin it like that, so it's kind of like off, it's not completely balanced in the middle, right? If you had that stick and it was kind of a little bit off balance and you spun it, it's going to have this wobble to it. But what it creates in space is what's basically called a double cone or a double right cone. But conic sections are based on this idea. Now, after this, I'm going to actually draw a picture. I'm not going to use my own hand drawing. I'm going to show you an image of what the conic sections are. But we could take most of what we've done, if you've had a class in geometry, and we can look at how do I make a geometric concept if I take these two double right cones that are inverted, and if I make them intersect with a plane. Now, that's going to be a little bit harder to draw, but if I do, let's say I go like this, I just make a plane here. That's not what I wanted to do. Let's do this. And then I need to make that transparent. All right, so pretend that this plane is floating around in space. And it's hard to, again, we're visualizing just space. If it intersects right here, and that point only, so basically it's coming across and just cutting at that one point, and it can be at a lot of different angles, it creates a single point. If I then take just this plane, and if I twist it, let's go like this, and I have it cut so that it just intersects, we'll still have it intersect at, erase that point there. We're still going to have it intersect right here. But then if it's at an angle like that, it might intersect just along this line and makes a line. Or I take that, I rotate it this time so that it's parallel, but then let's move it over here. And this is where it gets harder for me to draw and try to look and see what happens. So here's what I'm going to do. I'm just going to go ahead and go to this slide. So what I have is if I take this blue plane and I cut into this conic section so that the plane is parallel to this line, it makes a parabola. And those are things that we've been working with a lot when we're doing factoring of our quadratics. If I take this plane and I intersect it perpendicular to that line of symmetry that ran up and down, it's going to make what's called a circle. And if that plane shifts and goes down further, it makes a bigger circle. It goes up, it makes a smaller circle until it just hits right there at the middle, and then that would just be a point. If it intersects at a diagonal, it makes what's called an ellipse. So I don't know if you can read that. It's hard to read right there, but this is parabola. This is circle. This is an ellipse, which maybe in your past you called an oval. All right, more sophisticated language now, it's an ellipse. And then this one, the last ones, which we're very briefly just going to understand what the word is and how it looks as an equation. But that's a hyperbola. Application. That's what I get asked a lot. So what is this going to mean? How is this important? If I were to take a parabola, there's a very generic looking parabola. And if I were to take what's a point in that parabola called the focus is going to be somewhere right about there. And we're going to go a little bit into how to calculate that today. That's not the important aspect of what I want you to carry into the exam. But the point right there called the focus, when we talk about sound and light waves, if I have a light wave or a sound wave that starts at that point and goes out from that point, wherever it hits the parabola, it's going to reflect that direction. And it doesn't matter where, oh, that's a terrible looking line. It doesn't matter where it comes out of that point. Wherever it comes out of that point, it goes perpendicular. And this is the shape of your headlight on your car. Because if you put the light right at the focus, it's going to reflect out and go this way. It's also the shape of a satellite dish. Now, granted, satellite dishes are going to be a little bit of a bigger, right? They're going to be like a little bit of, okay, I'm just really struggling with drawing this morning. A much broader shape out like that. And then you'd see that point where, maybe it's like right here, ignore the other drawing, where that point is on the satellite dish, right? It's got the little thing that sticks out in the middle of the satellite dish. All the waves come into the satellite dish from wherever, and wherever they come in from, they'll hit that and bounce right to the focus. So no matter where the satellite is from, so again, the broader or more flat your satellite dish is, you can pick up waves from satellites that are way over in that part of the sky to way over in that part of the sky, and then anywhere in between. So this giant space. So figuring out like how many satellites do I need, the broader the satellite dish, the further away that angle can be where it's going to hit and bounce and get signal into your satellite dish itself. So those are a couple applications of parabolas. Circles exist in a lot of places. I'm not going to get much in there, but the ellipse is the other fun one. I say fun because I enjoy it. An ellipse is going to be about like this. It have 2 points called foci, because there's two. There's a focus and there's a focus. Together, two focus, a foci, just like two fungus, a fungi. Same thing. But here, if I have something, a sound or a light wave that emits from one focus, it goes to the other focus. And that's no matter what direction. If I go like this, slightly angle off of the midline, it's going to bounce directly back to that point there. This has a lot of applications. Now, if any of you have ever been to Washington, D.C., there's the hall, the Statuary Hall. The Statuary Hall in Washington, D.C. is elliptical. And if you stand at one foci and someone else stands at the other foci in this giant room and you whisper, they will hear it. As long as there's no one else in the room. I mean, you can even have a small amount of other noise in the room because it's not only are the walls elliptical, but the ceiling is too. So any sound that goes up is going to reflect all the way to this point here. Any sound spoken in this direction will go to here. And there's like this, I don't know if there's truth to it because I wasn't there. But back with the Founding Fathers, there was this concept. This was actually the hall where they did a lot of the debating for the House, for Congress. And there was someone who basically set up shop right there with their little desk so that they could hear what the other side was working on because they were at the other side or near the other side there. And basically just sat there with their head down and really trying to focus with all the other clutter of noise going on and hearing what was happening on the other side of the room. Practically, so if you're in the medical field and you end up working with people who have kidney stones, this used to be a method for breaking up kidney stones. So before they had a lot more of the sophisticated arthroscopic surgery and things like that where they go in and zap it now, they'll have like a little electrode. Before they did that, they would actually have this tub of water and they would sit you in a little chair right here so that your kidney is pretty much centered at that focus, at that foci. At the other foci, they would have a speaker and they would emit ultra low frequencies. So very, very low frequencies, and they would all come out here. And low frequencies go through bodies, right? That's why when you hear someone's bass really thumping, you feel it, right? So that's those low sound waves, you can feel them coming. But if you drop it so low that you can't even hear those sound waves, you'll feel them less, but in concentrated form when they hit this other spot, anything that's solid, like a kidney stone, will be vibrated to the point of shattering. So what happens, or what would happen is they would sit you down in this tub, ultra low frequency, you would sit there for a while. Yeah, it would feel weird. I've not had this done, my uncle had this done. And it would then break up those kidney stones into teeny tiny little parts that you could then pass out with less pain than a full-size kidney stone. All right, so that's another application of an ellipse. Ellipses are also, if you get into anything astronomical, how satellites, they're actually on elliptical orbits. Planets are on elliptical orbits. Pick just about anything that's out there. They're almost all on some type of or form of an elliptical orbit. Hyperbola, a little bit more nuanced for applications of that, but we're not going to spend a whole lot of time other than saying, oh, I look at that formula, I know it's a hyperbola. So there's the general formula for a circle, where this number and this number are the centers. So if I have an equation that's in that form, I can look at it and go, aha, H and K, that is the center of that circle. R is the radius. So in a general equation, it would be R squared. That looks is if I draw a circle, let's actually just make an XY axis here. If I do a circle, and I put the center of it right about there, where it looks like it is anyways. If that's the circles, and then I need to, let's go like that. Am I close? Closer. There we go. That looks about right. All right, so pretend now that I'm actually at that dot for the center. So that would be 1, 2, 3. 1, 2 up. So the center is 3, 2. It appears, if I drew my circle well enough, that distance right there is about 3. So if I saw a circle on a graph, I could say, well, I can now make the equation for the circle. It would be x minus 3, because that's the x coordinate, and it's squared. plus y minus 2 squared equals 9, because that's the radius squared. So a quick look at a circle on a graph, and if you can trust the graph, you could quickly then make make an equation for that circle. What we're going to do is go through if I have an equation, how can I find the center of the circle? And we're going to do that by completing the square. So although not one of our review questions for today, completing the square is something you need to know how to do. So we're going to do that now. If this were given to us, the first thing I would do is say, well, what kind of a shape is it? Because the coefficient of the x and the y are the same, that's critical for a circle. When I multiply it out, I will know that this will be a circle. But beyond that, if I don't know, it doesn't matter. We're still going to do completing the square in groups to solve for this. So this one's already set up so that I have my x's and my y's together on one side, numbers only on the other side. And then we go through the process of completing the square, and I'm going to do it first for this portion. So completing the square, x squared minus 2x. The process was I take this middle number. It will be the middle number. Well, I'll have a trinomial here in a second. Take that middle number and take half of it. Half of negative 2. So half of b, which will be half of negative 2, is negative 1. And then I square that and add it to this equation. So it'll be plus 1. Because negative 1 squared is negative 1 times negative 1. All right. And whatever I do to one side of an equation, I have to do to the other side. So I'm going to add 1 over here. Then I'm going to take this piece and bring it down. Plus y squared plus 6y. And I'm going to take half of b, which is half of 6, which is 3. I'm going to square it and add that to that side. And then whatever I do to the left side, I have to do to the right side of my equation. Now, on the left side, I have this trinomial. Let's go like this. That can be factored into x minus 1 and x minus 1. And this is the purpose of completing the square, is it's going to give me a perfect square. Because x minus 1 times x minus 1 is x minus 1 squared. The yellow will factor as well. Two numbers that multiply to 9 and add to 6. Now, if you're noticing, this number up here that we had for that negative 1, these are both negative 1, and that's true. That's on purpose. This number is 3, so this will be x plus 3 and x plus 3. And so this then becomes plus x plus 3. That's a y, right? Because this is a y. Sorry about that. Y. Just get so much in the habit of doing x's all the time. That's a y. It's y plus 3 squared. And then over here I have negative 6 plus 1 is negative 5. Negative 5 plus 9 is 4. So that equals 4. Now I have a circle in standard form. The center of that circle is at, I look in here, the standard form was x minus h. Is this minus? Yes, it is. So my h is 1. Here it's y minus k. Is this minus? No, it's plus. So that means I need the opposite sign. So I need, in this case, I need for my y coordinate to be negative 3. Another way to think about it, like we do with a lot of our factoring, what makes this 0? 1. What makes this 0? Negative 3. That's my center. And then my radius, in standard form, this is r squared, which means my radius is the square root of that. Square root of 4 is 2. So while this would be a challenging thing, I say, hey, if I want you to graph that, and you would oftentimes we go, well, x, y, let's just make a table of values. It's going to take you a long time to get that nailed down. This ends up being the faster, and where did that, this is not a 3, that's a 2. I get writing things down. I did the x plus 3, and then I wrote the 3 as my exponent. So this is x plus 3 times x plus 3, or y plus 3 times y plus 3 is y plus 3 squared. There we go. So that's a circle. So the ellipse is actually similar to the circle. How do I mean similar? If these two numbers were the same number, let's say they were both a squared or they're both b squared, and I multiplied both sides by b squared, this would be b squared, which is actually r squared. So how the ellipse and the circle are the same is, if they have the same number underneath, it's a circle. If the numbers underneath are different, it's an ellipse. H and K is still the center. That's still the center of my ellipse. We're not going to get into calculating the foci and where they're located. You'll do that in pre-calc, if you take pre-calc. All right. But what these numbers tell me is whether or not it's what you would consider to be, is it a horizontal ellipse or is it a vertical ellipse? No, those are not perfectly drawn. I know, it's a sketch. Horizontal by the fact that I mean that it's along this line. It's longer in the x direction. Vertical would be longer in the y direction. And the way I can tell it is it depends on which number is bigger. If the bigger number is under the x, it's horizontal. If the bigger number is under the y, it's vertical. And this length from the center to here is b. Because that's the direction in the y. See, there's the b squared. So if I square root that, that tells me how long it is that way. The distance to the left from the center, or to the right, this is a. In this one here, this is also a because it's the one in the x direction. This one is the b, it's the one in the y direction. How do I know it's in the x and the y direction? The a is under the x. The b is under the y. Since whatever number is under the y, that's my y direction. And that's how I know. So if this number is bigger than this one, the square root of b would be larger than the square root of a, and that's how I know it would be a longer direction in the a than in the b than in the a. So that's an ellipse. Calculating, and this is where if I have, we'll do it like this. Let's pretend those are my foci. That means my center is right here at -1, 1. If I could draw an ellipse, yeah, that was close. Those are the ends of the axes. As an equation, I'll have x minus a -1 because it's x minus h. Well, minus a negative is plus, so I'm just going to change that to a plus, squared, over something, plus y minus 1 squared, because the y is the y coordinate, y minus that, over something, and this will equal 1. And then I got to figure out what's the something that's underneath. So if I find out and say, well, how long does that appear to be if this is an accurately drawn graph? That's about 2. So that means in the y direction, it's going 2, so the number under the y is 2 squared. 2 squared is 4. And then in the x direction, it appears that I'm going 1, 2, 3. So underneath the x, it's that number squared. 3 squared, this would be 9. So conceptually, as far as like what a graph looks like, that's what those numbers are. It allows you to sketch it really quickly. Fun fact, if you want to create one of these on your own, just, in your free time, because I know you have a lot of free time and you're thinking, I know what I want to do with it. I'd like to construct an ellipse. You need to have 2 fixed points. So either put a suction cup on the whiteboard at 2 different spots, attach a length of string of, it doesn't matter how long, whatever length you choose. It has to be longer than, obviously, these. And then stick your pen or pencil on the, so if I had a piece of string, it would be kind of like this. It would go to here, and then down to the other foci. And if your pen or pencil is right here, and then you just start pulling it around the circle, around the ellipse, that string length doesn't change. So it's going to actually rotate around the end of your pen or pencil as it goes around. And you can actually construct an ellipse doing it that way. It's harder to do it like this as opposed to actually constructing one and showing you what I mean. But we're limited to the digital world. If you really are interested, go on, YouTube and say construct an ellipse. And there will be something and it'll show you how to make one. Probably a video of someone actually doing one in live person for how that would work and look. But you can make an ellipse doing it anything like that as you want, knowing where your 2 foci are. And now we are going to take this and convert it into an ellipse. At first glance, how do I know it's an ellipse and not a circle? The coefficient of the x squared and the coefficient of the y squared are different. And they're both adding. That's what makes it an ellipse. So when you get more comfortable with this and more confident doing these in the future, you look at this and go, oh, I know what shape that's going to be. Just looking at the equation, I've not done anything, but I know it's going to be an ellipse because these are they're different coefficients. That's a 1, that's a 4. And they're both positive. If they're both negative, also would be an ellipse. But for this case, we'll just go with this. And we're going to do a similar process of completing the square. My x's and my y's are together. My number is on the other side, so I can begin with the completing the square process. I'm going to bring this one down, x squared plus 2x, and then I'm going to do like I did on the other one. Half of b, which is half of 2, which is 1, square it. Well, 1 squared is 1. Add it to that side. Over here, I'll have 33 plus 1. I'm going to bring this one down. This is going to be a little bit more of a labored process because that first coefficient is a 4. So the first thing I'm going to do is I'm going to factor a 4 from both of them. Y squared minus 6y. Now I can do completing the square. Plus 4, y squared minus 6y. I'm going to take half of b, which is half of 6, or half of negative 6, which is negative 3. Then we're going to square it and add it. Negative 3 squared is positive 9. And on the right side, I am going to add 36. Wait, what? This 9 is inside the parentheses. The parentheses is times 4. So what I really added to this side of the equation is I added 9 times 4, which is 36. So on the right side of my equation, I'm going to have 34 plus 36, which is 70. On the left side of my equation, I will have x plus 1 squared plus 4 times y minus 3 squared. So I skipped that intermediate step like I did on the last one. But this negative 3 here also tells me, that negative 3, That's this negative 3. Y minus 3 squared. This positive 1, that's why it's x plus 1, quantity squared to that side there. And since I didn't bring this down, this is actually a negative 33. So negative 33 plus 36 is positive 3. Plus 1 is positive 4. Be a little bit different. All right, and then the last thing I have to do, since I know that this is not a circle, and the other reason why I know it now is this has a 4 out in front and this one only has a 1. An ellipse has to equal 1 in standard form. So I got to figure out, how do I make this a 1? I do it by dividing by 4. I divide by 4. I divide by 4 so that I end up with, as a final answer, x plus 1 squared over 4 plus y minus 3 squared, well, it's now over 1, equals 1. And then I look at this and I go, oh, well, it's going to be a horizontal ellipse because the x has a larger number underneath. So if I'm thinking just in my head what that might look like, it's going to be something like this. It'll be a horizontal ellipse where this distance here in the y direction is 1, square root of 1. The direction here will be 2, that's the square root of 4. So it's going to be a relatively small ellipse, but it's a horizontal one. Again, horizontal because the x has the larger number, and x is the horizontal axis. Y is the vertical axis in the y direction. Square root of 1 is 1, square root of 4 is 2. Yep. So the one difference in a hyperbola from an ellipse is the sign. Ellipses we added together. And when we did that, we ended up with an ellipse or something along those lines. Hyperbola, when I subtract, it ends up being like that. So if they were identical aside from the sign, if everything else was the same from an ellipse and a hyperbola, if this was an ellipse, this then becomes the hyperbola. The center of my ellipse is inside the ellipse. The center of my hyperbola is between the two vertices of the hyperbola. And the subtraction essentially takes this and breaks it out. Takes it right here and breaks it out, and that's why it becomes going in the opposite directions. And then I had this on here to show you how it would work. So hyperbola are a little bit more challenging because, which is another reason why we're going to stay with it right now, because it's not just, like if this is my center, and if I have one hyperbola going here, 1, 2, 3, 1, 2, 3, the other one's going to go here, where this distance here is 3 and that distance there is 3. So my vertex there is 1, 1. My center is -2, 1. This vertex right there is 1, 2, 3, 4, 5. -5, 1. The other part that goes into hyperbola is there will be a asymptote that goes here, which we're not going to calculate. There's an asymptote that goes here, which we're not going to calculate. Sorry about that. It's just a little bit harder to go through all the parts and pieces when all we're trying to do is get an overview and like a understanding of the structure of a hyperbola. But if this were my hyperbola, my equation would be, let's see, x minus a -2 squared. It's horizontal, which means my x is positive. Y minus 1 squared over equals 1. And the B and the A are harder to figure out because they're related to the asymptotes. So because this is only a sketch and I didn't do it really super accurately, we would not be able to determine those two numbers based on how I drew it right here. So like I said, it's a little bit harder to look at and do than, say, the ellipse or the circle or the parabola. But it's just, we can still do this. And I look at this and I say, 1, it's not a circle because the 4 and the coefficient of the x squared are different. It's also not an ellipse because the one is positive and the other one's negative. So there I know now it's going to be a hyperbola. If the highest power are opposite signs and not the same number, it's a hyperbola. The x squared is negative, so since the y is positive, it's going to be a vertical hyperbola. So think about it like the top of it and the bottom of it like that. But guess what we're going to do? Uh-oh, my number's on the wrong side. I need to move it over. So first thing first, we'll move it over. So I'll have 4y squared minus 16y minus x squared minus 2x equals 1. And then we will complete the square. First thing we have to do is take the greatest common factor out of the first term, minus 16y. The second one, I need to, now if you remember the equation for the ellipse, inside the parentheses, it was x minus h, which means I need the x to be positive, so I'm going to factor a negative out of both of them. X squared, it'll then be plus 2x. Then I can go about completing the square. 4, and this number here is no longer 16 because I factored a 4 out of it. That's now a 4. Y squared minus 4y half of b, which will be half of negative 4, which is negative 2, and then I square it, plus 4. On the right-hand side, I am not adding 4, I'm adding 16, because that 4 is inside the parentheses. So when it comes out of the parentheses, it's 4 times 4. That's the plus 16 to the other side. On the right, I have minus x squared plus 2x. Half of b is 2. Half of 2 is 1. 1 squared is 1, so it's plus 1. And this 1 is inside a parentheses that is trapped with a negative 1. So on the right-hand side, I will subtract 1. Because although I'm adding 1 inside the parentheses, realistically, when I took that negative out, if I were to distribute it back in, it's a minus 1. If I distribute this 4 back in, it's a 16. That's why it was the 16. On the right-hand side, I have 1 plus 16 minus 16, which is 16. On the left, I have 4 times y plus 2 squared minus x plus 1 squared. We've done this a couple times. I didn't do the intermediate step of factoring it, but it's going to be that because that was my b value, my half of b. Minus 2, that should be a minus 2. Because when I'm doing this, they have to add to a negative 4. But more realistically, when I did half of b, that's what that number is, minus 2. I need to equal 1, so I divide by 16, divide by 16, divide by 16 for a final answer of y minus 2 squared over 4, reduce the 16 and the 4, minus x plus 1 squared over 16 equals 1. It's a hyperbola because it's subtraction in between. The center is at negative 1 comma 2. What makes this 0? Negative 1. What makes this 0? 2. The x is larger underneath, which means it's a horizontal. Sorry, the y is positive. The y is positive. It's a vertical hyperbola. If this were an ellipse, it would be horizontal, but it's minus. Since the y is positive, it's a vertical hyperbola. And when I say vertical, I mean if it's graphed, it's going to be one up like this and the other one down like that, going up and down. And that's an ellipse. So with the parabola, that would be the general formula for it, where the vertex is h comma k. Right? The others we talked about, their centers. A parabola doesn't have a center, it has a vertex. This p number is related to what's called the directrix. All right. And again, you've probably not heard it stated like this before, but if I have a graph, and if I graph a parabola, the focus is right about here, and the directrix is an imaginary line right there. And this distance right here is p. This distance right there is also p. So the distance from the vertex up to the focus, the distance from the vertex down to the directrix is p. And what is the directrix, you say? If I take any point on my graph and I find this distance and this distance, they're the same. So going back to, doing geometry figures. And that's how a parabola gets defined. It's the set of all points, equal distance between the focus and the directrix. Not a real easy definition. Like a circle, all the points that are same distance from the same point. Very good. Ellipse, all the points whose distances between the foci, when added together, are the same. That wasn't a real smooth definition, but that's how it works. And then for a ellipse, it's the differences. But here for a parabola, which we've done before, you've graphed them, we've factored just a ton of them, but it's the set of all points. So this point is the same distance from the focus as it is from the directrix. And then the vertex is halfway between the focus and the directrix, which makes sense because if it's the same distance, well, this point is the same distance from the focus as it is from the directrix. P is that distance. All right. So what does that mean? Well, we just did one of those. I'm going to do, guess what? Completing the square. But in order to do it, I need to move my y's to the same side, my x's to the other side. So I'm going to add 6y to both sides. I'm going to complete the square on this right-hand side. X squared minus 8x half of b is half of negative 8, which is negative 4 squared plus 16. 6y plus 3 plus 16. What I do to the right side, I have to do to the left side. The right side factors into x minus 4 squared. The left side is 6y plus 19. And the general equation was y minus k times 4p equals x minus h squared. Which means I need to factor this left into 6, factor that out, y plus 19/6 equals x minus 4 squared. The vertex of that parabola is what makes this 0 for the x, 4. What makes this 0 for the y, negative 19/6. And although we're not going to do much with it, 4p equals 6, which means p is 3/2. So then I could find the focus, I could find the line of directrix. Biggest thing we need to do is just for this, finding out what my vertex is. So for these, what we're going to do is you're going to just look at them. Let me give them some numbers here. First, you need to ID the shape. Then, once you know the ID the shape, either the center or vertex, if it's a parabola, is it a horizontal or a vertical? And then anything else that you wanted that you might make note of for what you might know about what we've just talked about here. So this would be similar to what you would see on the exam. Either one of these or a couple of these saying, what shape is it and how do you know? What key aspects can you glean from just looking at this equation? Such as the center or a vertex, whether it's horizontal or vertical. Those would be the key items that I'd be looking for you to be able to go at and go, oh, it's one of these because of this is how I know. So for example, subtraction and subtraction. The only one that we have for subtraction is hyperbola, which means this one's a hyperbola and this one's a hyperbola. They're in general form, which means you should be able to look at it and find the center. The center of that one will be -1, -2. So what I'm going to do is I'm going to hit pause on the video that I'm recording. For those of you watching online, you're going to spend some time looking and going back through the other slides and the notes that you took to say, what is this one? What else do I know? Can I say what direction it goes? Is it horizontal or vertical? For shapes that requires it. And then when you finish that, you'll hit play again and we'll go through the rest of the solutions. Yep. So again, ellipse, because it's adding. Numbers underneath are different. The larger number underneath the x makes it horizontal, or you can think it's longer than it is tall, because the y is only 4. Center at 1, 2. 1 makes it 0, 2 makes it 0. The second one I already said was a hyperbola. All these bolas. Hyperbola, center. I look and say, biggest mistake people are going to make, they always assume the first one's x, second one's y, because it was up here, and we're always used to writing things as x comma y. You just got to really pay attention. There's the x. What makes it 0? Its center is 1, comma, 2. Has the same center as the ellipse up above. But I know it's an ellipse because it is subtracting. And then the larger number tells me that it opens up horizontally. Nope, that's only for the ellipse. Hyperbola, the positive number, the positive value, because this one's the negative, it's subtracted. So in a hyperbola, the positive one tells me direction. The y is positive, which means it's going to be a vertical parabola. Hyperbola, I keep using the wrong words. It's a vertical hyperbola, which means if I were to sketch quick, it would be like a hyperbola that opens up and down. The other one down below, oh, it's also y. All right. The center on this one, we already did, was that it's also a vertical hyperbola. because I know that it's a vertical hyperbola because the first term, the positive term, the one that's not being subtracted, is the y. Since the y is the positive one, it's going to be vertical, which means it's going to open up and open down. The negative means the x value will go left and right, making it a, there we go. All right. What else do we know? This one here is a circle because it's adding. Just like an ellipse, but like a circle is a compressed ellipse to the point where they have the same. So if you're like, oh, if you thought, oh, this is an ellipse, is it horizontal or vertical? Well, it's going the same direction up and down as it is left and right. So the width is the same as the height. Well, then that makes my ellipse a circle. And my center will be 1, 2. Because what makes the x, 1 makes it 0 here, 2 makes it 0 there. And it's a circle because the bottom number is the same and we're adding. Yep. If we were subtracting and had the same numbers, it would still be a hyperbola. So you can be a hyperbola and have the same numbers in the denominator. It's just that this would have to be subtraction. And I said there's at least one of each. Excuse me, which makes this a parabola. But how do we know just by looking at it that it's a parabola? There's something missing right here. Only one of them is squared, which means this is a parabola. It is a vertical parabola because the x is the squared value. If it were the other way around, if this were missing and this was squared, then it would be a horizontal parabola, where it would be like this with the vertex. All other things would still be the same in terms of the center, or in this case, the vertex is -1, 3. What makes this 0? -1. What makes this 0? 3. And that would be my vertex of that parabola. Because and I'll go ahead and erase this here because that's not true. Because the x was the squared value, that's what makes it makes it a vertical parabola. Had the y been squared, it would be a horizontal parabola. As we prep for exams and things like this, just good advice. If you're working on a problem and you really don't know where to start, but you know where it should end. Like, I can't complete the square. I don't know how to get this into standard form. But you know how to interpret what standard form means. But you're like, I don't know what to do. Honestly, you just make up an answer that is in the right form and then explain what the form tells you about the shape. So then I can go, well, at least they know at a minimum what's going on, but maybe you missed the idea on completing the square, so that way you're not losing out by not starting a problem. And I don't know how other instructors are, professors, classes that you take, but generally speaking, if you're like, I don't know where to start by writing down something that you do know about whatever the question is asking. And if it says, hey, it's part A and part B, and you use the answer from part A to get to part B, those are harder questions. So you're like, well, I can't get part A. Well, if you can't get part A, but you have a good idea how to approach part B, you make up a reasonable response. And by reasonable, it depends on what the context of the question is. Like if it asks for a solution, like, well, I can't find a solution there, but if this were the solution, this is then what I would do with, and then do it with whatever it was. So you can show like, all right, well, I missed that part, but I can still move on and demonstrate some understanding of other content that might be going on. Going to be better for you and able to feel like you're actually communicating what you understand and what you don't understand, and not getting trapped in a problem that maybe you just aren't thinking through the right way. That usually hits you about 5 minutes after you've left the door, and you go, oh, I think I remember how to do that now.